Good morning to all. In continuation of the previous lecture of the particle in a box, in continuation, I would like to discuss the some important other information regarding that problem. Let us start. Can you recall about that? In the previous lecture, we have discussed and tried to establish the important information that the energy is discrete in nature. Now, if you look the equation 9 which we have derived in the last, whereas the one parameter A star is not known, and let's try to evaluate this A star to have a proper solution of the problem. After solving this, we get the value of A star is under root 2 by A. That is also known as the constant of normalization, and substituting the value of under root 2 by A in the equation 9, we get a normalized wave function that is also known as the eigenfunction of the problem, and that is given as the psi x, psi of x is equal to under root of 2a sine of n pi x by a, where n can run from 1, 2, 3 and so on. Let's plot this function for the different possible states. First is to be the n is equal to 1, that is ground state, n is equal to 2, that is called the first excited state, and n is equal to 3, that is called the your second excited state. As you substitute the value of n, you will have the functions representation, and you may see the graphical representation of the function of the ground state is under root of 2a sine pi x by a, which is plotted like this. This is a plot of sine function, and you may choose the proper values of x, where somewhere it will get to be 0, somewhere it get to be 1, and substituting the value you will get the plot such as. Now other important parameter is probability density function. Let's say this is defined as the rho nx, that is given by the psi nx mod of a square. That's give us the general form 2 by a sine of sine square n pi x by a, where x lies between 0 to a. If you wish to plot, again substitute the value of n, that is for ground state, because the probability is the square of the sine function, so it will always have a positive loop, whereas in the case of the wave function it has the positive and negative loop in their graphical representation. I wish to quote a very important note here, which can be very useful in further study. This problem is very important to study the behavior of the free electron in conduction band. So in general, we try to get the eigenfunctions and eigenvalues. Remember, the wave functions directly does not tell any information, but try to find out the important physical parameter. We operate the im- corresponding operators over this function. Let's suppose if you wish to calculate the momentum, let's say you try to calculate the momentum that is defined as P, we operate the momentum operator, that is to be on the wave function psi of x, and it results the eigenvalue that is to be called the all possible eigenvalues can be computed through this operation. Similarly, you will able to calculate the kinetic energy of the system or total energy of the system. You apply the kinetic energy operator, that is the P notch square over 2m on the wave function. So you will get the eigenvalue of the kinetic energy operator. Now I am going to discuss some important numerical problems which can help you to visualize the application part of this problem, particle in a box. All the problem which I am going to discuss with you are based on the concept of the motion of the free particle, quantum particle in a box. The first question goes as the proton is confined in an infinite square well, so the width 10 Fermi. Remember, the nuclear potential that binds the proton and neutron in the nucleus of the atom is often approximated by a infinite square well potential. Somewhere you will find this problem also be stated as the free particle in a box, or you can say infinite potential well concept also. So what it needs, calculate the energy and the wavelength of the photon emitted when the proton undergoes the transition from first excited state to the ground state. And the second, in what region the electromagnetic spectrum does this wavelength belong? Conceptually, we have formulated our problem as in a particle in a box or infinite potential well. So this problem, the quantum particle is proton, so let's try to have the solution of the problem. First of all, let the eigenvalue of the energy of nth state is given as the En n square h square 8 mp, that is mass of proton a square, equals to, if I represent in a compact form, n square epsilon, where epsilon can take the h square over 8 mp a square, where mp is the mass of the proton. The electromagnetic radiation emitted undergoes the transition from the first excited state to the ground state. Let's say the delta E, E2 minus E1. Why we have taken the n is equal to 1 for the ground state? Remember, n cannot be 0. So the first excited state is n is equal to 2. Substituting this value, n square epsilon. So it has 4 epsilon minus 1 epsilon is equal to 3 epsilon. Substituting the value of delta E 3h square 8 mpa square, where delta E is the also represented as the hc upon lambda, that equates h. So the expression of lambda becomes 8 mpa square c 2h 3h, sorry. And substituting the numerical values, mass of proton 1.67, length of the box is given 10 Fermi, so that's by 10 into 10 to the power minus 15 meter, value of C 3 into 10 to the power 8 meter per second, and substituting the value of H 6.626 into 10 to the power minus 34 joule seconds, we get the value of the lambda is equal to 2.0163 angstrom. So more precisely, you can say that it is the order of the 2.02. And this wavelength, probably you may see, will lie in the region of the gamma ray. Therefore, it is a part of a spectra of electromagnetic radiation in which the gamma ray is present. Now, I am going to discuss the second important questions which can help you to understand that why it is not applicable to the quantum concept is not applicable in the macroscopic world. The first question goes like that: the a 1 gram marble is contained to roll inside a tube of length 1 centimeter. The tube is capped from the both end. Now it is suggested that the modeling this problem as the one-dimensional infinite potential square well, determine the value of the quantum number if the marble is infinitely given a energy of 1 millijoule, and also calculate the excitation to move a marble from the ground state to the excited state. Now, as the problem suggested, you model this problem as the infinite square well potential, one dimensional. So the energy corresponding to the marble is given to the E n square epsilon, where epsilon is h square 8 ml square, where m is called the mass of the marble, that is given 1 gram. L is given 1 centimeter, converts into a standard unit, substitute, and you will get the value of the n square, such as that is to be the approximately order of 10 raised to the power minus 28. 4.27 into 10 raised to the power minus 28. After solving, you will get the value of n. And you see, this is a extraordinary large value of the quantum number. And if it is an extraordinary value of the quantum number, let's try to find out the value of the energy which is exciting from the n to n plus 1th state, and you will have the second part of the problem. The delta E is computed n plus 1 square times of epsilon minus n square, which gives you, substituting the numerical value, you will get the 4.69 into 10 to the power minus 32 joule. See, this is a very small value tending to 0. 10 to the power minus 32. It is a very small order. So that's why it suggests that the large quantum number and the small energy difference associated to the marble, so it suggests delta E tends to 0. Therefore, the pattern is continuous for the macroscopic object. For this marble, the pattern is always be continuous. Now, question third, it's advised that the find the energy or the first three possible state levels for the free electron which is confined in a box with a width of the 10 angstrom. Also find the value of the wavelength of the electromagnetic radiation emitted when the electron make transition from the second excited state to the ground state. It is a very similar kind of problem. If you look at that, the formula which is going to apply there, the En is equal to n square times of epsilon, where epsilon is nh square over 8m a square. It is a mass of electron, and the problem is such as this electron is bouncing back between these two walls having infinite potential. Inside the box it is having a zero value of the potential. Ranging the value of 0 to a is 10 angstrom, and solving this with the help of the similar way, you will try to answer yourself. And this is the problem for the home assignment. And if you need the hint, please write me and try to answer yourself. One more very important problem I am going to discuss with you. Find the energy of the free moving electron in the box of the length A. If the length of the box is doubled, what would be the energy of the nth state in such a case? Look, the answer is very easy, and I am not narrating anything. You try to look at that. The energy of the nth state when the box is having length is En square epsilon, where epsilon is epsilon is given h square over 8m a square. So we have the energy En is equal to n square h square 8m a square. If the length of box is doubled, then the energy, you see this, the length of the box is doubled 2a, so that's why substituting in place of a 2a, we get the energy of the nth state is n square h square 32 m a square. With the help of the 1 and I can write this, the En dash is equal to 1 by 4 of En. So as the length of the box is being increased, you will always be having that the energy of the system is being decreased. In the same way, if you increase the mass, also the energy of the system is being decreased. So these are the important things which I wish to share with you. Thank you for today.